In this problem, we are going to calculate a force that will produce yielding under these specific loading conditions. We are going to use direction cosines to orient or describe the orientation of the force in space. We are going to use the vector representation of the moment to calculate the moments caused by the force in this section here, because we're interested to see what are the stresses caused at point P, and then find out what forces would cause the yielding at point P under the premise that the yielding strength of the material is this much here. Then we are going to do an analysis on how to see what are the stresses, normal and shear stresses caused by forces and moments. We're going to draw our infinitesimal element. We are going to then calculate all the normal stresses until we get our final total normal stress. We are going to do the same with the shear stresses. We have stresses caused by a force, stresses caused by a torque, and then this is the total stress. Then having those two stresses, what we're going to do, we're going to calculate the principal stresses on this planar case using this formula. There's a simplification of the three-dimensional case. And having the value for the principal stresses in function of F, we're going to use Tresca, or the maximum shear stress theory, failure theory, and von Mises to calculate how much are those forces. And in the end, we're going to find that forces, or the admissible forces for Tresca are lower than the forces for von Mises, which is something that we were expecting to get. So let's go to the beginning of the problem. The problem says that use Tresca and von Mises to estimate the value of force F, this one here, that will cause yielding at point P here. Consider the yield strength of the material to be 355 megapascals. Then what we're given here is a kind of a bent pipe or rod that has a diameter of 75 millimeters, and then from this point to this point, which is the bend of the elbow of this rounded section, is 500 millimeters, and then the height where the force is applied is 300 millimeters. So we have a coordinate system that is x, y, z here, and a force that they're telling us that is aligned with axis a little bit small, but it is here 54.74 degrees, kind of the angle between the force and the y-axis, 54.74 degrees, the angle between the force and the z-axis, but the angle between the force and the x-axis is not given. All right. Now, the way this force is oriented in space is by, or is how it is described in this point, in this case, is by using direction cosines. So we need to use the same restrictions that apply to direction cosines to find out how much is the angle of this force with respect to the x-axis. And we need to know that because the force is applied not anywhere near to point P. So it's applied here. So we need to know what are the effects of the force F in this section where point P is located. To do that, well, I believe that we can start doing some formulations here. So first, I need to know what's the value of this angle so I can know what are the components of the force in each one of the axes of the reference system I'm using. And then after that, well, we start doing, so what are the equilibrium conditions at point P, or in the section that crosses point P. So let's start with this. So determination, here, determination of angle between F and, let's try to delete this, x-axis. First thing we need to find out. Then we know, because of the way direction cosines work, they are not fully independent, the three of them. So we need to apply the restriction that constrains the, let's say, the orientation given by direction cosines, which says that, if I determine the cosine, direction cosines like L and then M and N, where this here corresponds to the angle with respect to the x-axis, this one is the angle of the vector with respect to the y-axis, and then this one is the angle of the vector with respect to the z-axis. Then the relation that exists among them is that the square of each one of them has always or must be 1 all the time. I should have written this a little bit smaller. So what does this mean? That if I want to calculate L, so I can say, well, L, which is the one missing, the direction cosine missing, and you're going to see what I mean by that, is going to be equal to, basically I need to take all of this, put it in this side, yes, and then subtract it from 1 and then square root of that. Let's do it. So I'm going to try to start a bit smaller. It's going to be then 1 minus, so this is cosine square of this angle cosine, so they are both the same, and if they're both the same, I can write it like this: square of the angle given there, which is this one. This is supposed to be A4 here. like this. Here it is. So how much is this? L, which is the direction cosine of it. So let's call it L equals to the square root of 1 minus 2 plus cosine of 54.74. Yeah. It says undefined. Why it says undefined? Strange. Sorry about this. I'm missing this square. Yes, there it is. So that's a small hiccup using the calculator. So this is 0. Let's call it 0.58. I'm going to try to use all the decimals found here. So most of the decimals, I'm going to call this 1,577F4. Now this number here is the cosine of an angle that I do not know. Yeah, it's equal to this, because this is the definition of direction cosines. So which means that this angle is going to be cosine minus 1 of this much, 774. Then that angle is going to be equal to, let's go to the calculator, and I can use the same one that is in the memory. So it's cosine minus 1 of L. Now look at this. Actually, the idea was this. So they are pretty close to the previous one. And actually, the purpose of the exercise is that these two angles, or this resultant angle, was pretty much similar to this 54.7 something. So we can call it like this, the same as this one here and this one here. Let me delete this because I want to see. So meaning that having that remaining angle, I'm going to write it down here. And that this was done on purpose. So this angle is 54.7, and let's use those ones from now on. I can come here and say, okay, then now that you have determined that angle, tell me what are the components of that force F. And then that's the next step. We need to find out the components of the force F, because remember that we need to go from components to stresses to principal stresses, and then apply the failure theories for each one of these cases to find out how much is that F, because we don't have the magnitude of the force F. So let's calculate here the components here of F. Yeah, decomposed onto X, Y, and Z. I can start using this some underlining here. Yeah. So let's see. Fx then is going to be who? It's going to be that F cosine of the angle that I have there. And let's use all this so we can make it even this much. Then Fy is going to be, it's awful, F times the cosine of this much. This is a 4, no, it looks like a 9. Yeah. And then Fz equals to this, like this. Meaning that all those three components are in terms of F, so which means that this is a very interesting case where it would make our life easier. So that's good. Now that I've gotten the components of this force F, I need to know what is the effect of F in a plane where point P is contained. Then let's see, how can we write it in green? Here. Trying to organize space. So effects of force here F on a plane that contains, this is like this, contains P. Yeah. Let me move this a little bit up like this. So what does it mean? When I want to analyze the effect of this force on a plane here, so I need to kind of move the force to that plane, but by moving the force, we need to take into account the moment that this force is created around this point P, because there is a vector between this point and the origin of this force. And we need that, so in the end, what's going to happen when analyzing this effect is that I'm going to have a replica of the force F and a moment produced by translating that force to that plane by using this vector, position vector here. So one of the easiest ways to determine what is the moment that this force produces around a plane here where P is located is by using it or calculating a moment in vector form. What is that? Well, I know that which I could use for example, this one here, this is a position vector. I'm going to call it R. Yeah. And this position vector has components on the 3 axes I'm using as my Cartesian coordinate system. So my vector R, position vector, is going to be equal to, then I'm going to keep millimeters, yeah. So it's going to be 500 millimeters in I, so I move 500 millimeters in the I direction, which is the unit vector aligned with the x-axis. And then I go up 300 millimeters in J, which is the unit vector aligned with the y-axis. So I'm going to have here plus 300 millimeters in the y-axis. And in the z-axis, there is nothing because the force, the point of application of the force, is basically in the plane, on the plane xy. It doesn't have any components in the z-axis. Then this is my whole, with green, position vector. And why need my position vector? Because the force caused by F, let's call it at the origin here, it's going to be the cross product of that and the force that I have just found. And what is that? Well, I'm going to omit the units just to save space, plus 300 millimeters. Oh, so that I was going to omit the units here. Cross J, cross, then this force, but the force could be written as a magnitude. It's going to be as the components of this force, or the projection of this force on the x, y, and z axis are equal, are the same, so the magnitude is the same, then I can just extract the magnitude from that vector and call it like this, cosine of 54.7 times the vector, the unit vector that represents those three Cartesian axes, and this one here. Then beautifully, I could, I like to say the word beautiful, I can come here and say, well, the moment is going to be equal to the cross product of two vectors. The first vector is going to be 500, 300, 0, because I have to count 0 in this formula, even though there is no any value spread on the z-axis. And then the other value is going to be this 1, comma 1, comma 1. Then again, why is 1? Because the magnitude, so y is, this is the vector that defines the direction of this force, is because the three components of force S, F, are going to be the same magnitude. Then it means that I can extract the magnitude from them, and which remains here is a perfect unit vector here. So my resultant moment is going to have components on the 3-axis, or in the 3-axis. So this moment is going to have, first, I need to multiply the magnitude, which I didn't do it in the calculator, but the magnitude is there, times who? Times this vector, 300 I minus 500 J plus 200 in K here. I want to delete this, yeah. I could shorten a little bit that and say, well, what about if I multiply M times the cosine of, can I write alpha like this? No, I cannot write it. I would love to do it, but anyway, it doesn't matter. M times then the cosine of 54.7. There we go. Yes, so we have those three values. Actually, I could write down something here. I can write that mx equals to, how to write it? Yeah, let's just spend some time writing it, because this is going to be help us to locate things. Times 300. Then my is going to be the same value here, 4.7, then times minus 500, and then mz is going to be the same magnitude. Cosine can be seen still on the screen, is this much, 4.7, then times 200. I did it like this because I want to kind of put it individually. I have forces already here, individual forces, I have individual moments. So then I want to do a small analysis on which type of stresses these forces and moments are going to create here on this point. But let me write down this moment, full moment, as a vector, just to have a 60.3 in I minus 267.1 in J plus, I believe this is the limit of the screen, 106.8, well, this is very close to 7, in K. Let me put some marks. So these things are red. These things are important, and these ones here. And why they are important? Well, because if I draw, for example, this plane here, how to call this here, stresses caused or developed. I used the previous one, developed. Let's use caused, produced, produced by forces and moments. Let's look at this. So if I draw that ellipse there, let me see if I can make it. Yeah, awesome, an ellipse here. So this is where P is located. And I can draw some axes here, meaning that this is one axis like this, then you have another axis like this. Yeah. Then you have another axis like this. Awesome. Where these are y. Oh no. Let me delete this because it's not. It doesn't want to. So I'm going to have y here. This is point P. Then this is x. And this is z. So let's see. This is a point I need to study. And what I'm going to do next is to draw a kind of a parallelepiped infinitesimal unit to represent stresses are going to be located there. Yeah? This is where point P is. So if I wrote down this, so this is point P here. Then in here, in that section, I'm going to have 3 moments. Most probably, for example, in x, it's going to be like this, positive mx. In y, I'm going to have a negative moment, which means it's going to go like this. Yeah, and this is my. And then in z is going to be a positive moment, which is going to be like this. And definitely, I'm going to have my 3 components, forces in 3 components. This is my fx. I'm going to have my fy here, and I'm going to have my Fz, all positive. So we need then to start asking questions to these forces, and the questions are, hey, so what type of force are you on the section, applied on the section? Are you a normal force, or are you a tangential force or a shear force? That's the first question. And then with that answer, we can go to the infinitesimal cube and ask, and tell, well, you are this, then you are going to create this type of stress here. For example, Fx is going to create a normal stress in this plane, in this area here. So I can right away say, hey, you know what? This force here is going to create a normal stress, and I'm going to call it normal stress created by force x. Then, I'm going to just kind of as a node, I'm going to draw only the stresses on the positive faces, okay? So stresses can be negative or positive, but I'm going to draw only the stresses on the positive faces, meaning this one, this one, and this one. And we know that in the negative faces, as I called them before, it's going to be the same, but in opposite direction. So then this is done. Yeah, this one. So this is done. Then Fy, this one. What type of force it is with respect to the section? Well, it is a shear force. So I mean, it's going to potentially create a shear stress. But now this is interesting. In analyzing shear stresses, we need also to take into account the position of the point we are analyzing, because let's remember that a section, I'm going to draw it here, for example, like this, under a shear force. I'm going to draw the shear force like this. Develops a shear stress like this, meaning that stresses at the end of the section are 0, shear stresses. Maximum shear stress is located at the center or in a position in between those two ones. Then if this is the case, the force or the shear force Fy does not create any shear stress at point P, because point P coincides with one of the outer fibers for kind of cases like this. It means that there is nothing to do with the Fy here, so it doesn't create any shear stress. But now, if we move to Fz here, Fz, so this is also a shear force with respect to this section here, and look at in this case, it is like this. Here, yes, here there is going to be a shear stress, because it's not neither at the ends of the section as seen from that shear force. So there is going to exist a shear force created by this force Z. And the shear stress is going to be something like this. I'll put it in green, like this. Yeah. So this is going to be a shear stress created by Fz, and that's going to have a value. So we have tackled all the forces. Let's go with the moments here. So this is tackled already. This is tackled already. So let's go with mx, the moment around the x-axis. So with respect to this section here, this moment is a torque. So then this causes or produces a shear stress in this section here of the area, which means that it's going to be coincident with this shear stress created by the FZ force. And I could then write it, well, you know what, here we're going to have, let me also put it like this, a shear stress, created by this moment, mx. And intuitively, you know that if there are those two shear stresses applied or acting on that face, then you just need to sum them up to find how much is the shear stress. Of course, due to the reciprocity of shear stresses, this is also going to be the same like this one here. So I mean, this one here, all of those two. Let me just put, starting to look weird. So we've tackled then this one also. So then let's take a look at the moment in the y, around the y-axis, this moment here. So this moment here, as it is applied, or kind of the way it is applied to this area here, it creates or it produces a bending moment. And that bending moment is going to produce a normal stress. But now this is very interesting because P is located in the neutral axis of a bending deformation produced by this moment y. So which means that moment y, or any bending effects created by this moment y, is not seen by P because P is located in the neutral axis of the section. So nothing happens there. So this is good to do this kind of analysis because you get to see what you are facing, what you need to calculate, and then you don't calculate extra stuff without needing them. Finally, we have moment Z, which also create a, a bending moment in the way it is kind of located with respect or applied with respect to this section. And yes, here is going to present the maximum or the largest bending moment you are going to have because P, according to the bending produced by Z, is going to create maximum compressive moment. You see? Oh, this is by Z, yeah, a maximum compressive moment. That's correct, yeah. Perfect. Now, what else? So if that's creating maximum compressive moment, it means that here we're going to have a minus sigma or normal stress produced by this bending moment mz. Which one that these two you need to calculate, and then these two you need to calculate. Now, if I clean this up a little bit, I'm going to have a planar case of stresses where this is too big. Let me reduce it. No, maybe I can reduce it like this. Yeah, a bit smaller. Like this, yeah. Planar case. And what we're going to have is normal stresses here. And this is going to be this one here. So the normal stress created by, produced by the actual force in X, and then the normal stress, or minus the normal stress produced by the bending moment Z. This is like I'm seeing it from above here. So this is the point of view here. Like this one here. Now it's becoming messy. Well, looking at it from above, and we know that these two gentlemen here are repeated also here. Just put it just in case. And then we're going to have shear stresses in this direction, which now it tells me that they are going to be, yeah, a bit positive. Yeah, they are positive. And they're going to be the shear stress caused or produced by this force plus the shear stress produced by this moment, which is a torque. Yeah? And of course, because of the reciprocity of shear stresses, this is going to be the same. So we have a planar bidimensional state of stress. Planar state of stress. Like this. Something I'm going to do is just to get rid of this. So I have more space because you guys are doing fine in here. Yeah. Then if I have this planar state of stress, it means that I could calculate those stresses and then calculate the principal stresses according to them. Yeah? So let's calculate each one of them. So let's start by this one. So this is a simple case where it's going to be equal to the force x divided by the area, and then this is going to be equal to the value that we know, cosine of 54.7 divided by the area of this circular section, which is going to be pi times d to the power 4 divided by 4. And then I have the diameter of that, which means I could just substitute it here, 75 to the power of 4. And then we can go to the calculator, because this is what we need to do here. So let's see here. I can call it, maybe I just, well, yeah, so it's going to be in the end cosine. Let me see how it's better represented. 54.7 divided by pi times 75, yeah, power of 4 divided by 4. Oh, that's a very small quantity. So can I, so if I leave it like, let me see something. I just want to make sure that, well, how can I transform this into a, yeah, it's going to be very big. Just trying to find a way to not use it like this. Oh, I have a big mistake. So this is why, because it's not the power of 4. Come on, it's not inertia or anything like that. Here, we're just trying to figure out how to make it as a fraction here. Yeah, but it's not telling me. It's not leaving me to do it. Let me just repeat it, because sometimes calculator is awesome, but when the user mess it up, so it's actually going to be 4 divided by pi times 75 square. Yeah, it is that. So this is going to be 1, 2, 3, 4, 5. Okay, so I can write it like, just not to make it that small. So this is going to be fx equals to, let me keep using fx. How much would it be that 1 divided by a, just to because I want to, okay, because I'm thinking that I could, instead of writing this bunch of decimals, I could here, I could write it like this, better. So it would be fx divided by this much here, 17.86. Yeah, better. I should write that I'm first working with the normal stresses here, so normal stresses. All right, so we have tackled this one we said that existed, and then we need to tackle now, we need to calculate the normal stress produced by the moment around the z-axis, which is this one here. Yeah, and this is a formula also that we very well know. Let me write here. So it's going to be that the moment, or the stress, what was the name I called it, mz, is going to be equal to that moment around the z-axis times the radius, then divided by this, the moment of inertia of it. And again, this is a formula of a very well-known section. And this is going to be, let's write down the moment here. What was the first one? Let's write complete. So f cosine of that angle, 54.74, times 200, times the radius, which is diameter divided by 2, then that divided by the moment of inertia, and the moment of inertia of a circular section is going to be pi, then the diameter, power 4, divided by 64. So how much is that? Normal stress caused by the bending moment, let me see, is going to be, I'm going to leave the f out, but I'm going to write down cosine of 54.74 times 75 divided by 2. Well, I should have written in the same order, but I have it here, but so multiplications are no biggie, times 200 divided by pi times 75 to the power of 4, yeah, divided by 64. And that is this much, and that much could be, I could use it in my formula as 1 divided by C, this one here. So I could write it like F. Let's write it a little bit more to the here. F divided by 358.72. Yeah. And there we have it. Awesome. So we have now our two normal stresses. I should get the maximum normal stress, and I'm going to call it here sigma, because I'm going to use it. Not the maximum normal stress, but the normal stress caused by these two elements. And I said that in this case, I'm going to have, I should have drawn this figure here. So let's draw, for example, here. For example, for the normal force, if this is the tube here, tube section, or the tube where P is located, is P, then the stresses there caused by the normal force, they're going to be kind of pulling like this. This is the way. This is a normal stresses or normal stress caused by the force aligned with the x-axis. Why? Because this force is pulling this section, and then that creates a normal stress like this in this section, like this. Perfect. Yeah. Then the reason I'm drawing this is kind of to visually see if I should, what should I do there? Well, here whatever happens is, well, however the stresses are imposed on that section, I need to account for that. So it's not that I'm trying to investigate what's the maximum stress in any part of the section, but it's a very good visual aid to see what's happening here. Now with this one, you should do the same for this. If I could copy this, bring it down and say, okay, how are the stresses caused by this moment around the z-axis? Let's see. Here and here. So we see that the moment around the z-axis is like this. So the upper part is going to be in compression, the lower part is going to be in tension. So this is going to be something like this. Let me try to write it like, oh, it was drawn curved. Like this. So this is compression, and in here tension. Yeah. We've talked about this, but now visually it's better to represent it in this way. Now, that means that the sigma value or the normal stress in that at P is going to be the subtraction of these two. So I'm going to consider this one as a positive one because it follows the convention that we are given for this cube here. And I'm going to consider this negative because this one is going to be in compression on the upper part. Lower part is going to be in tension, but no, we need to focus on this one. So then this one here is going to be, I need to transform the first force, so it's going to be something like F cosine of 54.7 divided by 4,4. This is the stress caused by the normal force, 0.86, minus this one here, 358.72. And how much is that? Let's go to the calculator and say, okay, I just need to divide the cosine of this by this 4417.86 and then subtract 1. Yes, 1, because I'm just taking F as common factor, this 358.72. It's giving me that, so it is a negative 1. Imagine that. Negative 1. Interesting. Then this can be represented as 1 divided by this E. Yes, this much. Is minus, here is minus F divided by this 376.38. Let me accommodate a little bit this, or order this. So let me just put it this like this, up, and let me delete this. Oh, delete this, and let me just write it down that this is the result of this, like this. Perfect. And I need this value because this is the one I'm going to use to calculate the principal stresses of this loading case. This and this. Just accommodate a little bit this. It's not working, but bear with me. F. Perfect. Now we have this. Next, let's calculate the shear stresses, and we said that there are going to be just two shear stresses, but in this case, both are going to be adding up. So it's not in the case of the normal stresses. And so here, shear stresses. Let's calculate first the stress caused by the force. We said that the force that was going to create stress, shear stress in this direction was going to be the force Fz, because this is the force that in here, when I draw this shear stress distribution on this section, in the mirror center, there's going to be the maximum value. Yeah? That's why we said that this is going to have a proper value. So the shear stress caused by the force Z is going to be equal to, also this is a very well known, so we don't have to calculate the first moment of the area on this section and then calculate the distance from the centroid of that area to the other part and the thickness. So it's already tabulated. So it's going to be 4 times the force in Z divided by 3 times the area of the section. And that's going to be 4 times, then actually I could write here, force cosine of 54.7 divided by 3 times the area, and the area is pi times the diameter square divided by 4. Now let's go to the calculator to see how much is that force or that stress. It's going to be then 4 times cosine of 54.7 divided by 3 times pi times square of the, is the diameter, just want to make sure I'm writing the correct force. Yes, and then I can divide that by this. Perfect, so it's going to give me that this shear stress, Fz, is going to be the force divided by this number that is given here, 5733.93. And we got this one here. You mark it like this. Now the shear stress due to the torsion, I would say, was the torsion in the moment x, or caused by the moment x. And we said that, how to put it here, that's right. So the stress caused by the torsion of moment x is also going to be a formula that is pretty similar to the stress caused by the bending moment. And that's going to be that moment x times the radius divided by the polar moment of inertia. And this is also a formula that is very well known that we could utilize here. So straight application of the formula. So moment x is this much here. Yeah? And we're going to have then F cosine of 54.7 times 300 times the radius, which is 75 divided by 2. Then we have the polar moment of inertia, and that's going to be pi times the diameter power 4 divided by 32. Then this moment, or this shear, that's why I keep saying moment, but shear stress is going to be, again, I'm going to leave out the force because that's my unknown, times 300 times 75 divided by 2. And here is going to be pi times 75 to the power 4 divided by 32. Yes. And this is going to be 1 divided by I here, 477. Awesome. So here, this is going to be, I have all the ingredients here, all the terms, and it's going to be the force divided by 477.82. I have the other one. Which means that my shear stress of the infinitesimal element is going to be the force times this 1 divided by this. And look at the shear force of the force created by the force is not as big as the shear force created by the torsion there. And this 1 divided by this 1.82. And how much is this? Let's just do it. 5, 7. This is a mistake again. Just notice it. 3, 3. Here. 33.93 plus 1 divided by 477.82. This much, and then again I can just use the reciprocal of this, which is 441. Then the total shear stress is going to be tau equals to the force divided by the results here, and it's going to be 441.06. And I'm going to mark it like this. Then having these two stresses, I can calculate the principal stresses. And then the formula that we've used before is going to be this one plus minus square root of this quantity here divided by 2, and this is square times this much, x. This is xz, yeah. I believe, yes, it's xz, like this. And I could just go and calculate this once here. For example, how much is going to be sigma 1? I can come to the calculator and try to apply this formula. So I can call Sx, let me see, I can call Sx as minus 1 divided by 376.3. So this is the normal stress in the x phase. And then I'm going to call shear stress is going to be, this is positive, 1 divided by 441.06. And I'm doing it like this because I need to leave that force out, because I don't know how much is that. So let's see. So the first stress is going to be this much. Just write like this. It's x divided by 2 plus then square root of Sx divided by 2. But let me go back a little bit, so to put the square term here. And sometimes this gives me some indetermination when I just change. So this is GeoGebra's way. So it's giving me undeterminate, because it's, of course, it's a square term. But as soon as I do this, okay, that should give me 0 because square. Perfect, and then I can divide this. Then this sigma 1 is going to be this much. F divided by 769.7. And sigma 3 is going to be equal to, let's do the same, but I can just maybe copy, duplicate input, and here I just put, let me see, yeah, minus. You give me minus. And then I divide that, and it's giving me minus this, which means that this is 252.73. I got my two principal stresses, which means that now I could use the failure theories to determine how much are those forces according to Tresca and according to von Mises. Yeah. Like this. What I'm going to do to get some space is I'm going to move this one here and put it, actually I'm going to reduce it a little bit, yeah, and put it here. Because here I want to calculate then F value according to Tresca and von Mises. I'm going to call von Mises like this. Then what Tresca says is that you need to compare let's say, your yield strength with the maximum shear stress on the element calculated using the principal stresses, and that's is a simple comparison of this. So in Tresca, what it says is that the maximum shear stress, which is this one, usually they put like, the absolute value, has to be smaller than this one here. Yeah. I know the yield strength of the material. I know this one, so I can calculate then that how much is that sigma 1. So we said that sigma 1 is F1, and I can call it like this. 1 divided by this 769.7 minus, but sigma 3 is negative, so this turns into positive, and this is going to be 1 divided by 252.73. This, and this has to be equal, kind of when yielding occurs, has to be equal to this value, which is 355, which means that the force is equal to, let's come here, and we can use a shortcut here. Let's solve this equation. X times then 1 divided by 769.7 plus 1 divided by 252.73. Yes, and that has to be equal to, how that you can see this, yeah, to 355. And that is 67.5 kilonewtons. I'm going to just shorten 67.5 kilonewton, the notation here. Excellent, my first result here, like this. Now for one misses, here it is, where is it? Just lost the pointer. Mark it like this, mark this like this. It should give me a little bit of a higher force, because what Misa is going to say is that, you know what, so yielding can occur at that point, then what needs to happen is that this much is sigma 1 square plus sigma 3 square minus sigma 1 plus sigma 3, like this, has to be equal to the yield strength. So how much is that? So if I wanted to write it completely, so it would be something like, it's going to be messy in space. So what about if I just write them down in the calculator and put the results here? Yeah. So again, I'm going to solve here, and actually can take f out of this equation because this is f squared. To explain a little bit, so I have f squared here, and then f times s is f squared, so I can take f out of the equation. Yeah, and f is going to be my times then. Actually, I can just write square root of sigma 1, then I'm going to put this one 769.7, and this has to be square. Square plus 1 divided by sigma 3. But sigma 3 is negative, so it doesn't matter because the square is going to turn it positive, but let's write it in any case. Yes. And this is square minus then sigma 1. Sigma 1 is, again, 0.7 times sigma 3, and sigma 3 is 1 minus 1 divided by this 252.73, and this has to be equal to 355. How much is that? Yeah, 74. So the force that in the end, just for the sake of keeping track of things, so I just did this, and then should I write it completely again? Well, yeah, let's write it because, well, it's going to be a long equation. So kind of is clear what I did there. So the force, according to von Mises, is going to be this much. It's going to be 74.86 kilonewtons, which is larger than Tresca, because just remember that Tresca is more rigorous in the sense of safety than von Mises. And this is the end of the problem. So we got those two forces, one according to Tresca, one according to von Mises, that according to the loading case will yield at point P. Yeah, what are forces? So let's summarize what's happening here. So first, we're given this kind of bent in the pipe here with a force oriented in space, the 3 axes. We are missing one value of the orientation of that force, but as we're using direction cosines to calculate, to represent the orientation of the force, it is easy having these other 2 angles to calculate the third angle, because the direction cosines have one specific constraint that needs to be met. So this problem is done in purpose for this case, and then it turns out that the angles, or the 3 angles, are the same, basically. Then I chose to represent it like this, so not to put 73 and 74, because here is marked as 54.74. So let's round it down basically to 54.7, so we can keep that. And then that's going to allow us to build, or to put the kind of my forces in this term. You see, they are kind of basically the same, and it's easier to isolate or to find out the value of f. So this is a didactic problem in that sense. Then what we did was to calculate what is the effect of this force in this plane here. Then when I have a force that is not near the plane where I want to see the effect of it, I need to consider the force itself and the moment caused by the force. And the best, or the easiest way to be sure about the moment that force is causing here is by using a vector representation of it, which R is the position vector that goes from the point O till the point of application of the force, and then the force itself, represented as a vector. When we did that, we got our 3 vector components from this part here, or in this part here, I would say. And then we did an analysis of what stresses cause these forces. So, for example, this force in F creates a normal stress in the face area, and so on. We analyzed what is the effect of the moments, bendings, which area of the pipe was in compression, which area of the pipe was in tension, how was the torque according to the moment in X, how much was the shear stress caused by the force. And we noticed that there was one force, for example, Fy, that it doesn't cause any shear stress because of the way shear stresses are distributed. We know that this force won't cause causes a shear stress in the section, but at point P that shear stress is 0. Then we found out that this is the way our infinitesimal element is represented, and we just went off to calculate each one of those stresses caused by each one of those remaining forces that cause stresses. So we did it for normal stresses, we did it for shear stresses, and then after having those normal or the total normal stress, total shear stress, we applied the formula to find out how much are the principal stresses here. We got them here, and then having the principal stresses, we went on to apply the maximum shear stress failure theory, Tresca, and then von Mises theory to determine how much is that force that caused yielding according to them. And we certified that for Tresca, the forces are lower or less admissible, the range is less admissible than for von Mises. And more or less that's the summary of the problem. If you have any questions or doubts, please leave it in the comments and then we can get at it and answer them.